new method, ERA, that estimates the branch length of the phylogenomic trees. So work was done in collaboration with Olivier Gasquel, Céline Scornavaca, Emmanuel Bouzry, and Fabio Pardi from the University of Montpellier, located in the south of France. As you know, we are in the phylogenomic era, and one of the important goals is to build the species tree using the maximum of available data. And we have to face some challenges. For example, in this plot, we can see that the genes are not present for all the species, and we know that every gene has its own history, and we have to account, for example, for gene rate heterogeneity. The method are presenting is not exactly building the species tree, but only doing the estimation of the branch length of the species tree. There are three categories of phylogenomic methods to construct the species trees. The supertree methods use construct the gene tree for every gene element, and then they combine the gene tree to construct the species tree. Another alternative is to use to concatenate all the gene alignments and to use the usual phylogenetic methods to construct the species tree. And the third kind of method I am particularly interested in are the distance lattice method. For this method, you estimate distance matrix for every gene alignment, and then you directly compute the species tree from these distance matrices. If we are looking at our problem of branch length, you can compute branch length in the concatenated framework, but these methods are computationally heavy. The supertree method usually don't look at the branch length in the entry and don't give branch length in the outputs, and the distance path method are potentially able to give branch length. So before to present my method, I will introduce some properties of phylogenetic trees. Every phylogenetic tree can be represented with a distance tree vector, and for example, for this tree, the distance between the taxon 1 and 4 is 0.4. That is the sum of the branch 0.1 plus 0.1 plus 0.2. Another property is that the tree distances can be written as a product of a topological matrix multiplied by the branch length vector. The topological matrix is a binary matrix that codes for the shape of the tree. And if we come back to our problem of estimating branch length, this is for when we have only one gene as input. It's usually done with the weighted least square method, and the aim of this method is to find the branch length that gives the tree distances as close as possible to the input distances, minimizing this criterion. And we are able to find the branch length of the species tree, of the gene tree, with a complexity in the order of n cubed. And so we wanted to generalize this method in the case where we have several genes in inputs. So we made the assumption that every gene, and you see approximately the same tree up to a scale factor alpha cap, and up to the removal of some lineages. So once we have found the scale vectors, we can see that all the gene trees shows approximately the same branch lengths. And once the input distances are scaled, we can look for the branch lengths. So we have two kinds of unknowns, the scale vectors and the branch lengths. So more formally, our method takes as inputs n distance matrices and a given fixed topology. And our objective is to find the branch length of the topology tau and the scale factors of the gene trees. To do this, we minimize this criterion, which is a generalization of the weighted least square criterion I showed you just before. And we need to have a constraint on the scale vector to find the solution. The method outputs the branch length and the gene rates that are the inverses of the scale vectors. If we solve the minimization problem with the Lagrange multipliers method, we end up with this linear system, and finding the branch length and the gene rates can be done in a complexity in the order of n cubed plus n multiplied by n squared. And what is important in this complexity is that it is linear in n the number of genes. So we are able to deal with phylogenomic data sets where n is in the order of several thousands. So now I'm going to show you some results on the simulated data sets with 500 genes. So to compare our method, we had to adapt some phylogenomic distance path methods, SDM stars, and the D-star method was designed for the estimation of gene rates. And we as well compared our method with applying the maximum likelihood method on the concatenated alignment. So here are the plots for the accuracy of the estimation of the branch length. In the horizontal axis, we have the model branch length, and in the vertical axis, we have the differences between the estimated branch length and the model branch length. So a method is good if it gives the branch length close to the zero red lines, and overestimated the branch length above and underestimated the branch length under. And as well, we have looked at the accuracy in the estimation of gene rates. In this case, we have the gene rates in the horizontal axis, the model gene rates in the horizontal axis, and the ratio between the estimated gene rates and the model gene rates in the vertical axis. The results are showing that the best method is applying the maximum likelihood method on the concatenate, but it costs a lot computationally. And we can see that for the super distance matrix method, this method has a problem for the estimation of the gene rates, and the D-star method is good for its purpose of estimating the gene rates, but not for the estimation of branch lengths. And our method is quite good for both tasks. So now I'm going to show you other results on the real data sets. The Orthoman databases is composed of ortholocus genes of mammals. And for these data sets, in inputs we have 7,000 genes, And the topology of input is this topology of the 40 mammals present in the database. And for this data set, what is very interesting is the running time of the different methods to estimate the branch length in the maximum likelihood framework on the computation of the gene alignment. You need around 2 days and more than 100 gigabytes memory. So it's hard to do with personal computer. And with our method, we need a few seconds and only 200 megabytes. For the accuracy in the estimation of branch lengths, this time we don't know about the real branch lengths, so we took as references the best method on the simulated datasets, and we found the same kind of results that in the simulated datasets. Super distance matrix method has problems with the estimation of gene rates. The distal method has problems with the estimation of branch lengths, and we are relatively accurate at both tests. And to conclude, I have presented to you a new method era that gives branch lengths to phylogenomic trees. Our method is relatively accurate in both the estimation of branch lengths and of gene rates, and our method is fast and can handle with very big data sets in a few seconds. Thank you for your attention, and if you have some questions.
So I think we have a couple of minutes time for questions. Are there any questions?
So what's the framework of the software?
It's distance as the software, and you have two alternatives. You can give it the distance estimated directly from the gene alignments, or you can give the tree distances that was computed with the trees coming out from the super tree methods. Two solutions.
Thanks.